Hello, everyone, and welcome to AISC's webinar, Blast-Resistant Design of Steel Buildings. This is Part 2, Blast-Resistant Analysis and Design, presented by Aldo McKay. Today is March 24th, 2016. My name is Christina Harbour. I am with AISC's Continuing Education Group, and I will be moderating today's presentation. I'd like to introduce today's speaker. Aldo McKay has 14 years of experience in the security and protection engineering field and currently serves as Senior Engineer and Principal at Protection Engineering Consultants. At PEC, Aldo regularly manages physical security and blast-resistant design efforts for numerous buildings for conformance with Department of Defense, federal facility, and VA facility requirements. In addition, Aldo has managed and led research efforts for the Department of State looking at the lateral response of steel-braced frames under blast loads. Aldo also has extensive experience in performing progressive collapse analysis and design of buildings using both GSA and DoD standards, including assessments and retrofit designs for existing steel structures. Aldo earned a bachelor's degree in engineering from John Brown University and a Master of Science degree in structural engineering from the University of Texas at San Antonio. Welcome, Aldo, and I will let you take things from here.
Thank you, Christina, and thanks everybody for the invitation. I'm very excited to be your presenter for today's Part 2, Blast Resistant and Analysis Design. Some of you that attended last week's session were able to listen to Kurt gave a great presentation on blast loads. And today we're going to be focusing on the next step, which is taking the blast loads and applying it to the buildings and showing how we end up with, member sizes and connections that can go into the construction. My understanding coming into this webinar was that the audience for today, in terms of understanding of blast resistance design, was very wide. So we try to prepare a presentation that if you're not very familiar with blast design, you're going to at least be exposed to the main terminology and concepts. So next time you come into a project, at least you know what questions to ask. And if you're familiar with blast resistant design, we do get enough into the technical details that hopefully this webinar will allow you to maybe clarify some questions that you didn't quite have clear. And of course, we're going to have questions always that we can answer later if some additional clarification is needed. So today we're going to start with the talking about the general design approaches and the main assumptions that we have in blast design. We're going to look at the different criteria and references. We're not going to cover those documents in detail, but it's good to add them here because you can always come back to the presentation and use them as references. Then we're going to go into the design steps, for designing a building to be blast resistant. And once we get into the portion of the presentation where we start talking about the blast design of components, we're going to be seeing some examples and talk about the single degree of freedom and some of the other methods. We're going to finish the presentation with the right here. We're going to be talking about at the very end on how do we go about designing frame response and the different methods for doing that. Here's a list of the acronyms that we're going to be mentioning throughout the presentation. We don't need to explain each of them. We just wanted to have a reference sheet for you to come back and, if we're talking about SBES or PDC, you can come back here and, get familiar with what that means. So first thing that we wanted to do today, for those of you that have never seen a blast-loaded building, was to show you a video of an actual test that we did recently to, put you in the right frame of mind so that you can start wrapping your head around the type of loading that we're dealing here. So I'm going to play the video a couple of times, and there will be while it plays, I want to point out a few, 2 or 3 important aspects of blast loading on buildings. As you're seeing right now, hopefully, the blast wave, as it propagates to the building, it happens very quickly, and it loads the building, causing all different types of response modes. I mean, The elements of the structures are getting pushed in every direction, up and down, are being compressed, are being pulled in tension. So the main thing that we need to, the very first thing that I want to point out is the level of simplification that we go through in terms of analyzing a building to blast loads. We look at the building on a component by component basis, and once we look at one component, we further simplify by only focusing on one mode of response. So I'm going to play the video again, and then you can keep that in mind as you see the blast wave propagating. It breaks the facade, it's going through the building, so the columns, the braces, they're all getting loaded in different directions. And when we analyze those elements, we're going to simplify at the component level, and in addition to that, we're going to be focusing mainly on the flexural mode of response. The next item that I wanted to bring up as we look at this video again is the fact that in order to load a component, the component needs to have a member that collects the load and transfers it to the member. As you notice here, this building, the facade or the envelope of the building was not hardened, so it fails really quickly. And when the blast load enters the occupied space, there is no significant damage to the members. That's because none of them have collecting elements that were collecting the blast load and transferring it to the members. The final 2 points that I want to make is that in an actual blast-resistant building, the envelope is the first line of protection. So a lot of the structural elements that make the lateral system and the gravity system are protected from the blast loads. So when you're going to be designing a building, you're going to be concentrated on the exposed elements, which generally occur in the roof of the building. And finally, I want you to pay attention as I play it one more time. The lateral response of the frame itself is minimal. We see a lot of shaking happening, and that's from the ground shock, which is a component of a blast load that Kirk mentioned. You can design for that. It typically requires the blast load to be very, very, very large. But in terms of like the sway response of the frame itself, it's minimal, and that's generally because of the differences in load duration and the natural period of response of these buildings, and we're going to cover that later in the presentation. So hopefully, again, given the variety of the blast-resistant familiarity that we have in the audience, we wanted to show up a video at the very beginning, give you a good idea of how these buildings get loaded by blast, and then from here we can start diving more into the details. So here are the main design approaches. Once you're faced with a blast-resistant design problem, you have 3 or 4 different ways that you can go about it. First, we have what we call the energy or closed-form solutions. These type of equations are advantageous because you can basically solve them by hand, and all you're doing is you're having to find an equilibrium of the energy from the blast load and the strain energy of the system. The downside of the closed form energy solutions is that your component needs to be clearly in the right and applicable response realm. In other words, it needs to be clearly controlled by the impulse of the blast load, or it needs to be clearly controlled by the pressure of the blast load. And we're going to talk about that once we get into we're going to see an example for a closed form energy solution, and we're going to discuss it a little bit more detail later in the presentation. Next, we have the single degree of freedom approach, which it's the most typically used design method, at least in my experience. And that is because it's a good combination of explicit consideration of dynamic effects, plus it's simple enough that allows rapid design so that you're trying to keep up with the design phases. We need to keep in mind that when we're doing a blast resistant design, a lot of times you're part of a design team, and maybe you're in a design build effort, which are very fast, or even a design build, you have to be able to produce rapid and efficient designs so that you keep up with the design team. Single degree of freedom analysis gives you that capability of providing that balance between accurate designs and quick. Next, we have the equivalent static load. As the name says, it's a method in which we calculate an equivalent static load that is based on the ultimate flexural dynamic of the member. In other words, we calculate the reactions, the maximum reactions that those members can transfer before they fail. This method is generally used to calculate connections and components at the end of a load path. So we're going to talk about this later when we talk about the frame response, but one of the methods for looking at the frame response of a building is using the equivalent static loads of the envelope components and applying them statically in the lateral directions. Finally, we have the dynamic finite element method. This requires the use of more sophisticated analysis tools that can account for nonlinear material properties and nonlinear geometry. It's generally saved for very special conditions. For example, if you're designing an interior detonation for a mailroom or sort of like inside a parking garage, or you have a very close-in chargeway right next to a column, and you want to try to take into consideration different modes of response that are not going to be exactly flexural, you might need to employ this method. But for most designs, in terms of like the typical buildings, and single degree of freedom or closed energy solutions or chart methods should be adequate for you to get an efficient design. So what are some of the main design assumptions? So when we're dealing with blast, we need to keep in mind that these loads are very fast. And so the strain rates, the speed of response are so fast that it causes the material to behave in a stronger manner than what they are specified. So typically, if you have a piece of steel that is specified as 36 KSI, you're going to see that it's going to behave more like a 42, 45 KSI. You're going to see an increase in strike on 10 or 20% sometimes. So once you're dealing with blast design, you want to keep in mind that your material strengths are stronger than what the lower bound specifications say. Next, you want to know that we work in the ultimate capacity region. So you can picture a beam with both ends fixed. Typical conventional design, you have to limit the capacity of that beam to the first yield that happens at the supports. When we're doing blast loads, we push components onto the ultimate capacity. So if you have a fixed beam, you're going to yield at the ends, but you still have a capacity until you finally reach the collapse mechanism when the hinge force midspan. So you're going to have material increases. We're going to go to ultimate capacity. Typically, we want components to respond in a ductile manner, so we try to make the connections strong enough to develop the capacity of the member. And finally, the design is not based on stress limitations, like moment capacity or shear capacity, but rather is controlled by the deformation limits, which we're going to see later are usually expressed in terms of support rotation and ductility ratio, which is a measure of the plastic deformation. Now, let's just talk a little bit about the design criteria and references that you're going to encounter out there once you start doing these designs. First, if you the more typical design guidance for buildings in the United States in terms of providing loads and performance are going to be the Department of Defense USC 41001, which is the DoD minimum standards. You can see it right here on the right. That applies to all military construction in the United States. Next, if you're dealing with federal facilities, courthouses, FBI buildings and such, you're going to be using the risk management process, which is this blue document right here. And some of the other more common type of designs that involve blast resistance design are the VA facilities, which they have their own set of criteria called the Physical Security Design Manuals. And finally, if you're doing petrochemical designs, you may need to use the ASCE design of blast resistant buildings and petrochemical facilities. These are the documents that basically define the blast requirements for the different industries. And again, once you go into those documents, you are going to find how to apply the blast loads, what are the response limits for your components, and some other requirements that are specific of that industry. If you're looking for more comprehensive guidance and just want to dig really deep into the technical information as far as like how the equations were derived, the testing that went behind some of the approaches that we have right now, you probably want to go to the USC 33402 or 33401. I think those are the most comprehensive set of documents that we have in terms of providing blast resistant education and knowledge behind the procedures that we have today. I think the SS methodology manual, which we have right here on the right, is a good balance between having enough detail to explain why things are the way they are without being overwhelming. So if you're in that range where you're familiar with blast loads, you're just looking to take it to the next step instead of understanding a little bit more how do we apply the tributary width and how do we check connections and things like that, I recommend you read the methodology manual for SBES because it's a very good guidance. And finally, we have more industry criteria that has been developed that provides really good guidance on the application of blast loads and the design of blast-resistant building and components. Right here on the right, we have the Design Guide 26, which is a very nice, very well-developed document that provides examples on closed-form solutions, on how to use single degree of freedom analysis of components. It also has analysis of frame systems and discusses the application and development of blast loads. So this is another one that it's a good start for you if you're looking into learning more about blast-resistant design before you get into the more comprehensive ones that we covered before. So let's just talk about what are the general design steps for blast design of steel buildings. As we show in the video, the first line of defense in a blast-resistant building is the envelope. So every time you're going to be designing a blast-resistant building, the main thing you do at the beginning is just make sure that you provide an envelope. It could be a glass curtain wall or any type of facade, metal studs, girts, metal panels, CMU walls. That's the first thing that you design. Obviously, you're always coordinating with the lateral supports and things like that. After you design your envelope to resist the blast load, that envelope collects the loads. Remember, we talked about that. For a member to be efficiently or effectively loaded by blast, it needs to have members that collect the load and transfer it to it. So the second step is when it's probably what we're going to be concentrated in this presentation, is just looking at the analysis of the exposed structural members in a steel building. Because as we're going to see, we have a few illustrations later in the slide, a lot of the members end up being protected by the envelope. So generally, your exposed members are going to be in the roof area, and sometimes if you have some spandrel beams or perimeter beams that are providing support to curtain walls, you need to look at those too. And in some cases, it's not very common actually. You may need to look at a column design. When you're designing these members, we're going to look at the single degree of freedom approach. As we mentioned before, we also have closed form manual calculations type of analysis using energy approach. And we're going to discuss the equivalent static load approach, which is the one used mainly for connections. Finally, we're going to talk briefly about the frame system analysis and just kind of like introduce you to a couple of approaches that you could use if you were faced with that challenge of performing a frame system analysis on a steel building. So let's just talk about that step 2. We're assuming that we already have a hardened envelope around our building. So let's just look at the steps when you're starting to design the blast steel components. We at the very beginning when we show the video, we talk about the simplification of the blast resistant design. You have this massive amount of energy that loads your building, and it pushes us in all different directions and causes compression, twisting. So we look at that and we simplify it, and we look at it on a component by component basis. And when we look at a component, we concentrate on the dominant motor response. as I mentioned before, typically we want to make sure that components are designed in the flexural mode of response because it allows the components to bend and absorb a lot of energy, which results in efficient components that are not very expensive. If we were trying to design against blast loads, keeping components in the elastic range, it will be just too expensive. So the first step is to determine your blast load. We're going to talk about that and how we do that. Next, once you have your blast load, you want to have a member to start that you're going to analyze against that blast load. The design process for blast loads and for blast resistance design is interesting because we don't usually start from zero and start looking at blast resistance right away. I've always said to my architects clients and structural engineer clients that the best place for incorporating a blast resistance into your design is somewhere, believe it or not, somewhere right at the 65% stage. Because at that point, most of the components have been designed for conventional loads and serviceability and some other requirements that are equally important. So you can grab that design, you have some components and geometry that have been defined, and then you just analyze them against the blast load, and then you can tweak as needed in terms of connection capacities, spacing, member strength, to make sure that your structure is blast resistant. The way you do that is generally using single degree of freedom analysis, but as we're going to see here in an example, you could also be using closed form energy solutions, which can be done manually if you have MathCAD or Excel or something like that. Once you have calculated the response of your component, you're going to compare that to the response limits, which are generally expressed in terms of support rotation and ductility ratio. That takes care of your flexural response. You also want to look at shear, make sure that you have enough shear strength and connection capacity to develop that moment capacity and indeed design a ductile member. And then you change like I said, you check the connection here at the end as well as the shear against that equivalent static load. So let's just talk about determining the blast load. Typically, the blast loads in a project are going to come in a specification, or if you're doing a DOD, it's going to tell you what kind of charge weight and standoff you have to use. So the main two approaches for determining your blast load is it's usually specified as a pressure and impulse pair. We're going to see that in the next slide. Or you may calculate it based on an explosive weight and a standoff. There are many tools available for doing that. I mean, there is charts that allow you to go and figure out the incident impulse and pressure and then convert that into a reflective pressure and impulse. But in today's kind of blast resistant design world, I mean, there are enough tools available that you should be able to just plug in a number and get the loads that you need for your design. When you're doing the charge weight and standoff, sometimes you can account for the angle of incidence. Kirk covered this last week, where if you're not hitting your component at a sort of like 90-degree perpendicular direction, there will be a blast reduction for the angle of incidence, and then some software allows you to account for clearing effects, which is the reduction that happens when the clearing weight happens at the edges. And sometimes you need to consider the increased effects of re-entering corners, where blast loads will enter the corner and reflect between the two members, basically creating a longer duration, which puts more energy into your member. Another way of determining the blast load for your component is using the dynamic reaction from the connecting member. And as needed, you may use more complex approaches, like if you have an internal detonation again, and you could use something like Blastex. It will calculate shock and gas pressures. Again, you want to pick the tool that best suit your needs. For most blast resistant design buildings, you're going to be dealing with a pressure and impulse pair, or an explosive weight and a standoff distance based on the site layout. So pressure impulse pair is this is what it looks like. It's typically assume a triangular shape As you can see here, the impulse is the energy under the pressure time history, and is generally the area of the triangle, so it's 1/2 the duration times the peak pressure, and that generally gets applied over the tributary area of the member, as we can see here. If this is your member that you're trying to analyze, the supporting component, you will take that triangular load that we just saw, and you would apply it over the tributary width, which in this case is denoted as B. The other method is using the dynamic reaction, which is more efficient and better for you when the ultimate resistance of the supporting component is significantly greater than the supported component. That can be confusing, so let's just take a look at that. What we're saying here is that if this black line, which is the supported component, is very strong in comparison with this member that is spanning between the two of them, it will make sense to analyze the supporting component, the black line, using the dynamic reactions of this weaker member. The reason for that is, by this being weaker, it's going to respond and absorb a lot of the energy, so the dynamic reactions are going to result in a reduced response of your member if you were to compare it versus putting the full load on this member based on its tributary width. So good examples of the dynamic reactions sometimes are when you have open web joist on steel beams at the roof. You can gain a lot by just using the dynamic reaction of those members instead of putting the full load on those girders and beams. So now let's just talk about the energy solutions, which is one of the methods for analyzing the blast response of a component. Again, we have two cases. What we're trying to do with an energy solution is we're trying to match the energy from the blast load to the strain energy that is stored in the member. So in other words, the energy of the blast load could be coming from the total energy under the blast load, which is the impulse, and then the strain energy in the member, it's calculated by taking the area under the resistance function. So if you have a component that is in the impulsive region, meaning your load duration is so small compared to the natural period of the member, then you use the kinetic energy of the blast load, which is the impulse, and you equate that to the strain energy of the member, and you can calculate the maximum response. If you're in the pressure sensitive region, in other words, your load duration, this right here from 0 to TD, is so long compared to the response of the member that is effectively a static load on the member, the energy from the blast load is going to be controlled by the peak pressure. So you use that value to equate to the strain energy, and then you can solve for the maximum displacement based on that peak pressure. So impulsive sensitive region, you're going to be controlled by the impulse of the blast load. Pressure sensitive region, you're going to be controlled by the pressure, the peak pressure right here of the blast load. And we're going to see an example of that in a little bit here. The next method for, we talked about a component, you determine the blast load, you determine your component, you analyze the response. We just saw what the closed form energy solution is. The next method is the single degree of freedom approach. So before we get further into the single degree of freedom approach, let me just say that to thoroughly cover the single degree of freedom approach, you could spend like the full hour just talking about that. So here we just wanted to introduce you to the terminology, the main concepts on how the single degree of freedom is developed, so that you know what parameters of the single degree of freedom relate to more common parameters on a beam, such as moment capacity and stiffness. I mean, if you want to learn more about the single degree of freedom, you can reference any of the guides that we gave you in the previous slides, and some of them have some pretty good guidance on how to, pick your time integration method and how to determine your stiffness, your load mass factors, and so forth. So in a single degree of freedom approach, we're simplifying the blast response of a member down to one motor response. Hence, we call it single degree of freedom. So if you're looking at this fixed beam right here, once that beams get loaded by blast, that beam is gonna wanna bend as is shown right now. It might try to shake in shear. It might try to twist. It's gonna have different modes of response. So what we do is we pick the dominant motor response, or the motor response that we want to design that element to behave in, and create a single degree of freedom that represents that one motor response. So if you develop a single degree of freedom to track or trace the flexural response of a member, you do not want to use that to assess the shear capacity or the shear response, the dynamic shear response of the member. So you need to be careful that once you develop a single degree of freedom, you know what it represents in terms of like the real behavior of the component. So in this case, we're developing a single degree of freedom that is tracing the mid-span deflection of a fixed beam. So you turn that into a spring mass system where the mass represents the tributary mass of that beam at this one point, and the stiffness represents the strength, Ru, and K, the stiffness of the actual beam. When you develop a single degree of freedom, generally you have three main parameters that define your behavior: the stiffness, the ultimate resistance, and the mass, and that creates what we call the resistance function. So you can see it right here. This is just a generic resistance function just to show you the different shapes that you can have. This one in blue, you have a stiffness, sort of like elastic range, then you yield, and then if you have adequate connections, you can take into account the tension membrane behavior, which gives you more strength. You always think of your resistance function in terms of like, if you were to take the area under that curve, that will be the energy that you can absorb. So you can see that if you account for tension membrane behavior, you have a lot more area under that curve, as opposed to like if you were just doing a simple bilinear type of resistance function, because your connections do not allow for a tension membrane, then you will just come here and then come down, so you lose a lot of energy. One of the main things that we wanted you to be familiar with when we talk about single degree of freedom is understanding the parameters and how they relate to, like I said, to common parameters in using structural design of steel element. Typically, you want your component to be in flexural response, like I said. So you're gonna wanna calculate the stiffness of your member, which is generally based on the deflection equations for different support conditions and for different loading conditions. And then your ultimate resistance, which is directly related to the moment capacity, the dynamic moment capacity of your element. So there are tables like this one in many, Guide 26 has them, structural dynamics books like Biggs have them, where the author has used the beam equations to solve for the different components of the single degree of freedom system. So right here you can see for a fixed beam, the elastic resistance is 12 M, because that's what causes the hinges to form at the ends, and that will be the limit under conventional designs. But then the ultimate resistance, it's even higher because it takes into account the final hinge that occurs at midspan to form your collapse mechanism. Right here you can see the different stiffnesses for the different regions when you're in the elastic region, elastoplastic region, and finally the elastic region. And you can see the equations used to calculate your equivalent static loads at the ends. Something that I didn't show here was the transformation factors. By the principle of energy conservation, typically the work done by the external force, the energy stored in the component, and the strain energy of a component that is loaded by blast has to be in equilibrium. So you need to do energy equilibrium methods to make sure that the single degree of freedom system is it has an equivalent energy absorption as the actual response, and that is done by the application of load mass factors that get applied to the load and to the mass, but typically they're combined into one that is called the LM factor, KLM factor, and that gets applied only to the mass. And we're going to see that here when we do the first example. Next, in terms of the properties for calculating your moment capacity, again, you need the moment capacity of a steel component to be able to calculate the ultimate resistance. When you're calculating the moment capacity of a beam, your yield strength is going to be your dynamic yield strength. And the way you calculate your dynamic yield strength is you take the minimum static yield strength and you apply two increase factors. The first one, the factor C, is the dynamic increase factor, which, as I mentioned earlier on the basic design assumptions, it accounts for the strain effects. These components are responding at a lot faster rate, so they're actually stronger than the lower specified value, so you get that increase. And the second increase factor is what we call the average static increase factor, or SIF. This is a factor basically to translate the lower bound specified strength to a more realistic strength. In other words, if you have a piece of 50 KSI steel, the 50 KSI yield strength is a lower bound specified. Chances are that if you take a piece of that steel and you do a coupon test on it, you're going to find out that the actual strength of the element is 5–10% higher. So that's why when we're calculating the dynamic moment capacity for blast resistant design, we typically increase it by these values right here. This table comes from the SBET's methodology manual, but it can be found in several of the design documents that we mentioned before. So typically you can see here that if you have 50 KSI steel, you're going to get a 5% increase for static increase factors, and then almost a 20% increase for strain rate effects. So let's just talk about the design of plates. Typically, plates are used for doors and containment cells. They're pretty good at stopping fragments, but they're not used as sort of like a main structural elements. One of the things to keep in mind with plates is that for them to develop the full plastic moment capacity, they need to be pushed really far into the plastic region, at least 5 times the initial curvature. So when you're going to calculate the dynamic moment capacity of a plate, typically you need to use the average of the section and plastic section modulus, unless you're going to be going so far into the plastic region, a ductility of more than 7, that means you're like way over here. That would allow you to take full advantage of your plastic section modulus. And other than that, you can see the equation is just very standard for calculating moment capacity of a component. You multiply the section modulus times the yield strength. When we're talking about beams, those are the most typical members that you're going to find in a building. The strengths could be 36, 50 KSI, although 50 KSI are more typical. Usually you want to make it respond in a flexural, ductile way. You're going to hear me say that a few times during the presentation. Want to make sure that only compact sections are used. And a lot of times they're braced in the compression flange, but you need to be careful for roof members. Sometimes you may need to add bracing in the bottom flange for rebound, because that becomes their compression flange. So the bracing is important because it reduces your moment capacity. So the way you calculate your moment capacity for a beam in blast resistant applications, again, you use the same equation, a little bit different than the plate though. Like the beams can develop the full Z sooner into the plastic range. So typically, if you're going to be going past a ductility of 3, you should be able to use the full plastic section modulus. Most of the response limits that we use in DOD, ISC, VA designs, they all come from the PDC Protected Design Center, Technical Report 0608. And unless you're designing for very high level of protection applications, you are allowed to go past a ductility of 3. So it's very common for design of steel beams to use a full Z value when you're calculating your moment capacity. Then this equation right here is just to show that lateral bracing has an effect on your moment capacity. You can basically use the same equations from the AISC construction manual to calculate what that reduction does. There are tools out there like SBES that take that into account when you're calculating the blast response of a member. So this is a good time to look at a quick example. If we were to design a roof beam that is supporting a deck subject to downward blast load. So let's just say this is an actual building, and we look over here. This is the beam that we want to design. It's right here. So it's about 12 feet span. And then let me just make sure, like, this might not be typical, but it's just an example to illustrate the process. So we have a span of 12 feet. This deck, again, spans side to side between these members at a spacing of 5 feet. The beam is W21 by 14, grade 50. We have the span, we have the spacing, and then these are the geometric properties of the beam. And for this example, we're assuming that the roof cladding has a weight of 5 psf. So we know all that. This is all information that you can get from your drawings, and this is just following the exact same process that we would in an actual design, where somebody say, hey Aldo, we're at the 65% design. Please let me know if I need to make any changes to my roof. They will send me their 65% set of drawings. This is information that I will pull from there. So you go to the next page. First thing we do is we have the blast load, and we're going to be using an energy solution for this first step. So we want to be able to, the first thing we want to do, we want to derive all the parameters that define the load and that define the single degree of freedom and resistance function. So we know that the load is an impulse of 80 psi millisecond, and it has a peak pressure of 35. We know the impulse is the area under the triangle right here, so we solve for TD, and we get that the duration of this blast load is really short. It's only 4.5 milliseconds. I mean, that's pretty quick. Next, we're going to calculate the mass. And for this example, we're working on units of pressure because it allows us to compare to SBES, which is the main tool that we use internally, and SBES works in units of pressure. You can work your single degree of freedom solution in any way. I know BICS, a lot of the examples in BICS are based on linear loads. You can turn it into a sort of like one load without not having the linear effects. It's up to you. You just need to be consistent with your units. So for this beam, we know the self-weight is 14 pounds per linear foot, but we're saying our tributary width is 5 feet, which is the spacing. So that gives us a weight per unit area of almost 3 psf, 2.8 psf. On top of that, we have the supported roof cladding weight, which is 5 psf. So notice that when we're calculating the mass, we just take the actual weight. We don't add any sort of like 1.2 and any load factors. We just take the actual weight that is going to be displacing with the component. So the total weight is 7.8 psf. We know our gravity, so force equals mass times acceleration. We solve for mass, and we get a mass of 140 psi millisecond squared by inch. Again, these units are just so that we can compare to an example in SBES later, but you are able to use different units. You can work it in linear or in units of pressure. So next, we want to calculate the elastic stiffness. For a supported beam, we go to the beam equations for simple supported beam. It's a 5 over 384. K is basically W over the midspan deflection. So you solve for that. We have our E, 29 times 10 to the 6th, and the geometry, the moment of inertia from the tables. We know the span, we know the beam spacing. We can calculate the stiffness of this member to be about 7.6 psi inches. We're almost there. Next step on developing or determining the single degree of freedom parameters is calculating the ultimate resistance of a simply supported beam. You know, we use the beam equations. The moment of a simply supported beam is generally WL squared over 8. So we solve for that W, which represents the RU. So it's 8 times the moment capacity, the dynamic moment capacity of the beam divided by BL squared. The dynamic moment capacity of this beam is going to be the FDY, which is going to be the 50 KSI times the CIF and the DIF, static increase factor and dynamic increase factors, times the plastic section modulus. Obviously, we're assuming that we were going to go past a ductility of 3. So you calculate your dynamic moment capacity, and you can calculate your ultimate resistance, which is 7 psi. Now we're getting closer to do the energy solution. We need to apply the load mass factors. These are the transformation factors that I mentioned earlier that are used to make sure that the single degree of freedom in terms of energy is equivalent to the actual element. These factors have been developed for a variety of loading and support conditions, and they're available in the Guide 26 from AISC. The SS Methodology Manual has them. BICS, which is an excellent book on structural dynamics, also has tables, so you can just pull them up for a simple supported beam with a uniform load. So you put the LM factor. We take the value for the elastic range and put it on the mass and calculate our natural period of vibration. So notice the natural period is almost 24 milliseconds. And with that information, we already have our ultimate resistance that we calculated before, and we have our stiffness. We can calculate the deflection at yield, which means this is the deflection that at that point, if we keep going further, we're going to be in the plastic region, meaning we're going to deform and we're not going to be able to bounce back to the initial deformation. So as you can see, there is a number of steps. Even though it's a manual solution, there is a number of steps that you need to go through. So, after you do the first one, maybe you set up a spreadsheet and they can go a little bit faster, but it's a little bit of work involved in doing this calculation. So since we're going to do an energy solution, the first thing we want to check is that we are clearly in one of the two response realms. So generally, when your load duration is a third or less than the natural period of response of your component, you're going to be controlled by impulse. Or if your duration is at least 10 times the natural period of your component, you're going to be controlled by pressure. In this case, we are way less than a third, so we're pretty good in the impulsive region. So we can use the equations for impulsive control energy solutions. So we go back to the equation that we showed before. We have the kinetic energy from the blast load on the left, and we have the strain energy for the component on the right. We solve for X max, which is the maximum midspan deflection. We fill in the values. We already developed all those values, and we get that load, 80 psi millisecond load, is gonna result in a 4.6 inches of deflection at midspan of that roof beam. Now let's just compare that to the SBET solution or any single degree of freedom approach. In SBET, it does the calculation of the single degree of freedom parameters for you. So we would enter here the span 12. I know the picture is a little bit small, but hopefully you can see it in your notes a little better. We enter the spacing, which is 5 feet on center. It's a simple beam. We have flexure, and then we enter the beam that we're analyzing right here in this area, and it uses that to calculate the single degree of freedom parameter, and it develops a resistance function like this here. In this middle area of S-base, we can enter the load. I mean, you can see it's the same pressure and impulse in duration as we had before. And then you run the time stepping solution, and we get we get the same load right here. You compare that, make sure that you put your load right, and we can see that the maximum deflection is about 4 inches. So it's a little bit less than what we calculated with the energy solutions. The difference could be because of a couple of reasons. I think it could be some rounding errors in the moment capacities and RU values that SBAS is calculating. But I think the main reason for the difference is because even when you are clearly in the impulsive region, you're never going to be fully 100% controlled by impulse. In other words, the peak pressure may have a little bit of an effect. And whereas if you run a single degree of freedom analysis, you're accounting for the load explicitly because you're solving for it at every time step. So I think that's where the main difference between the two results, 4.6 with the energy solution and 4 with the single degree of freedom comes from. But still, you can see that you get a pretty close result, and both are pretty good methods. Again, the tools these days are so advanced that it's probably faster to run a single degree of freedom than to do a manual calculation. So now let's just talk about columns. We mentioned that in terms of designing a building to be blast resistant, you're going to be looking at your exposed members, which generally are the roof, maybe some perimeter beams, and occasionally you're going to have columns. Columns may be loaded in two different ways. The first approach for columns is when you're looking at it for axial capacity. You can picture a top-level column that is resisting a blast-resistant roof. You're going to have an axial demand on the column that is basically going to be the equivalent static reaction from the blast-resistant roof member. And you check that by just using standard AISC equation capacities. You may use them without the fee factors, but that depends. I've seen it go both ways. It really depends on the specification for the building that you're trying to design. I know that the ASD, LRFD are being combined, but we left this note here because we see this all the time where when you specify a equivalent static load based on the dynamic moment capacity of a blast resistant member, those loads should be treated as a factor load. So you want to make sure that you at least are comparing that to LRFD capacities. We have some structural engineers that still use the ASD approach, which gives you, if you're not looking at the load side of the equation, you're just looking at the capacity side of the equation, the ASD load can be less. So generally, if you're going to be comparing an ASD capacity to a equivalent static load, you get to increase it by about 1.5 or 1.7. The next way a column gets loaded is when it gets loaded by lateral blast loads. And in this case, you're going to have combined axial and lateral loads because the column is going to be obviously carrying axial loads, but now you have the blast load that is pushing on it, side to side in the lateral direction. This is the point that I made earlier in the presentation. It is very common in steel construction to have the cladding and facade to protect the interior of the structure. So columns are not really loaded, or at least their tributary loaded width is significantly reduced. One of the main considerations for design of blast resistant steel columns is the base plate. Generally, you wanna make sure that you recess the plate because that could be the weak point. Again, we're trying to develop the full dynamic capacity of these things, and if you don't have a recessed plate, you can have a bolt shear failure, as you can see here in this test. You can see on the right, the column, it's bent in all different ways, but it's a significantly curvature, so it clearly went into the plastic range, and the bolts right here weren't able to take the load. So generally, it's a good practice to make sure that you do a recess and sort of like grout fill compact so that the lateral reactions are basically taken by shear and straight into the floor diaphragm. Now let's just talk about the equations for these beam columns. they're really derived from Chapter H in the AISC specification for structural steel buildings. Basically, you have the equation and you make it equal to 1, and then you solve for that moment capacity that is going to be reduced based on the blast loads that are based on the axial load and the axial capacity ratio, which reduces the moment capacity. We're going to look at an example of that later. So these are the equations basically from the SBETS manual, and as I said before, they're just derived from Chapter H in the AISC specification. Generally, I have yet to see a column that it's outside this range, where the P acting on the column pushes it past 20% of the P critical. The reason for that, at least in my experience, is again, a lot of the interior columns where the heavier loads are expected are protected. So any column that you might be looking at could be on the top floor, so the P is reduced. Plus the P that you use for design of extreme events is generally reduced. Some DoD documents like the PDC TR0608 recommends you use 1 times D plus 0.35 life. The ASCE stream load events recommends you use 1.2 D plus 0.5 L. Either way, it's a reduced load compared to like the 1.2 plus 1.6 life load that you use in conventional design. And then again, these are the equations you solve for M, and that's your reduced moment capacity that you use to calculate your ultimate resistance in your single degree of freedom system. Let's just talk about response criteria. If you remember that slide where we defined the steps to analyze a component, we already talked about the blast loading. Then we talked about how you pick your member and where do you start. We analyzed the response. We looked at the energy closed form method, and we looked at the single degree of freedom approach. And now we want to make sure that we talk about the response criteria, which is when we compare the response to the acceptable limits. The response limits are based on deflections. Typically, you calculate the deflection of your member to the applicable criteria. This type of response limits, they change based on the material and the component type. And there are different sets of response criteria, but for the most part, the typical designs, V8s, Department of Defense, and federal facilities, they all refer to the PDC TR0608, which we're going to see an example of what those tables look like here in a 3 or 4 slides down. So here's what a response criteria looks like. You have 2 parameters. The first one is support rotation. The way you calculate the support rotation is you're going to, again, we have developed all these single degree of freedom modes that represent the mid-span deflection of these different types of beams and under different loading conditions and with different supports. So we're going to grab the measure peak deflection, and then we're going to use the inverse tangent, simple geometry calculation to calculate the angle of rotation at the support. That's one parameter. The second parameter is the ductility ratio, which is the ratio of the maximum deflection divided by the deflection at yield. Again, this is a measure of the level of plasticity. The reason that you use the 2 is just to control different combinations that you could find in a building. Just off the top of my head, you could have a very ductile, very long span that it could deflect, a beam that is like double story, going 24 feet, that it could be deflecting, 20 inches and it's still in the elastic range. Well, in that case, you're going to be limited by the support rotation because you don't want anything to deflect that much because it could cause stability problems. So that's why in some other cases you might have a very short beam in which you want to limit the amount of plasticity that you allowed in it. So that's why you use a combination of support rotation and ductility ratio so that you can keep the response very consistent throughout the building, knowing that the spans and the configurations are going to be different. So these are some of the documents that you can use as reference for learning more about response limits for single degree of freedom components. This is a document that you heard me mention a couple of times, and it's by far the most mostly used in sort of like classic, what I call classic blast resistant applications for these three industries right here: DoD, VA, and ISC. But then you can also refer to 33402 and 33401, and they have some additional information. And these limits may be a little bit different because these are for like hardened structures. They're more robust, so their deflection limits may be more strict. These are probably a little bit more relaxed because we're not trying to design to the level of these two documents down here. So going back to the roof example that we saw recently. Let's just say, we have that roof beam, and we're going to be using the results from the energy approach, which was like 4.6 of deflection. And we want to see if we satisfy the response level B2 per the Protective Design Center Technical Report 0608. So first thing we calculate is our ductility ratio. Previously, we had calculated the maximum deflection and the elastic deflection, so the ratio of those two gives us a ductility ratio of 5.1, more or less. And then, based on the span, we used half of it. It was a 12-feet span, and then we used the inverse tangent of the maximum deflection divided by half of the span, and we calculate a support rotation of about 3.7 degrees. So if you were, again, going through the process of a real case example, like I mentioned before, that was the structural engineer gave you the building and told you, hey, am I okay for the blast requirements? You run your analysis. You're calculating that one component has 5 ductility ratio and it has 3.7 of support rotation. You come to the PDC response limits document and you look at the B2 limitations. This is a member in flexure and it's compact. The limits are 3 and 3. So we calculated a ductility ratio of 5 and a support rotation of 3.6. So it's not okay. So in that case, what you will do is pick a different member, redesign it until it works, and then you coordinate with the structural engineer or the architect to make sure that it gets incorporated into the final construction documents or the final design documents. In the PDC criteria, going back to columns, generally you only consider the combined effects like we saw before when the axial load acting on the column is greater than 20% of the PDU. This is what I mentioned earlier. That document recommends you use the dead loads plus 35 of the life load. Depending on the document, you might be able to use 1.2D and 0.5L. But the approach is going to be the same, basically. PDU, again, is the ultimate dynamic outside compression capacity, which means you're using the dynamic strength factors and everything that takes it up to the ultimate level. So let's just talk about the shear and connection design, which is the very last step. We went through the whole process, and now we know how to check the flexural response against the response limits. We know when it works. We know when it doesn't work. The last step, which is probably the most important one, is make sure that we ensure a ductile behavior. So to do that, we want to make sure that our component has adequate shear capacity and that the connections are strong enough to develop the full flexural capacity of the member. This is when we use the equivalent static load approach. VS is the maximum shear force that a beam can transfer based on their flexural capacity, and the way you calculate it is you take the ultimate resistance, which is the RU of the member. Again, that comes from the dynamic moment capacity. You multiply it by the width, because in this case we were working in units of area, the span, and these KS factors. They're basically factors for the different support conditions. If you have a simple beam, KS is 0.5 because the load goes equally to both supports. If you have a fixed simple beam, one gets 0.625 and the other support gets 0.375. So these KS factors, They're provided to you in the same documents, BICS and Guide 26, SS Methodology Manual, but they're also just standard shear distributions from beam deflection equations. So the shear strength of members, the way we calculate the shear strength of steel members, it's very typical. It's very similar to the way we do it in the AISC construction manual. I mean, the ISC construction manual uses .6. The FY, in this case, it uses this equation, .55. Steel is based by the elastic buckling of the web, the elastic yielding. The yielding of the web is what controls the shear capacity. And for most cases, we're in this range where the HT ratio for the web member, it's under that value. There are some equations for the very seldom cases in which we are outside, and those can be found in this document and some other documents. I think 34001 also has some guidance on that. And once you calculate your yield strength, using the .55 of the dynamic yield strength, the dynamic yield strength includes the A and C factors, which is the static increase factor and dynamic increase factor. You use the typical equations, from the code to calculate your shear capacity. So, for example, if we have a W10 by 100, A992, it has a FY of 50 KSI. This is the web thickness and the depth of the member. First thing we do is we calculate our FDV, which is going to be .55 times 50 KSI times my CIF and my DIF, and then this gives me the actual shear strength. And then we just use the standard equation for the web area times the FDV, and we get a capacity of 260 kips. So it's in this case the phi factor is 1, so we don't need to apply it. We're going to talk about that later. Depending on the design that you're working on, some specifications allow the inclusion of LRFD phi factors. I think we should include them when we can. Some other specifications tell you to use just 1 because they realize we're already designing for ultimate capacity, so there is some conservatism already. So this is kind of what I'm discussing right now. When we're doing a connection design, you want to make sure that it receives the ultimate equivalent static load to allow that ductile behavior. In some cases, you need to be consistent. If you analyze your member to include tensile membrane because you needed that added strength in order to resist the blast load, you need to make sure that you include those forces when you're designing your connection. Sometimes you're going to have combined tension and shear, depending on the component that you're looking at. And this right here is important. A lot of the components under blast loads, they get hit by the blast load, and they use that internal energy and inertial moment to resist the blast load. But then, even after the blast load sweeps away, they rebound because that energy gets released. So that rebound sometimes can cause the connections to fail. The typical rule of thumb is if your component is remaining elastic, you want to design your connections for the same force inward and outward. If you have a component that is yielding, typically the outward reaction is going to be less, so you may use 50% of the inbound load. You could also look at the dynamic reactions from your single degree of freedom and get an idea for that reduction of the inward response versus the rebound response. But definitely, the rebound is something that you want to take into consideration. If you go back to the case of a column, where you don't have a lot of edge distance coming out of the building, you're going to have a different capacity, during rebound that you have for inbound. So just keep that in mind when you design your connections. Again, the approach varies. I've seen specifications that allow the use of 1 as your phi factor. Some other ones require the phi factors. Some may actually tell you not to use any increased factors in your material strengths and design using the lower bound strengths. The typical recommendations that we make is that you design for your equivalent static load. So and you use that load as a fully factored design load. Obviously, I have said this many times already, the strong connections are the best way to include ductility into your design. And depending on the motor response, you may or may not increase the material strength. The starting increase factor, I think you can add it because that's a representation of a real strength of the material. The dynamic increase factor depends on the mode of failure that you're looking. If you're looking at something brittle and sudden, kind of like a shear over on a weld or like shear through a plate or bolts, you probably don't want to use your DIF. If somehow you have a connection where you're sort of like bending a leg or of a plate or something like that, where it's more of like a bending kind of behavior, you may actually use the DIF to gain a little bit of strength on your connection design. Here's an equation, just a quick picture, just wanted to show you what a kind of like a failure connection of a connection looks like. These are some old tests on some steel frames. This is a very typical retrofit for windows on existing buildings where the wall cannot take the loads. So you retrofit them by putting steel frames behind them, and the windows connect directly to the frame. In this case, the connections were not properly designed to remain attached to it was a concrete beam, so it created some sort of like concrete breakout failure. Again, that's not desirable because that frame will come out of the whole thing will come out as a system and fly into the occupied space. We always want to make sure that we remain connected at the connections. So now let's just look at another example to sort of like try to bring everything together that we talked about on the design of steel components. On this example, we have 500 pounds of TNT about 60 feet away from a building, and we want to analyze the response of a steel column up here in the third level. If we look at the side elevation, this is our column. It's about 15.4 feet, the span. And for this example, we're assuming that the cladding in front of the column spans horizontally, so the loaded width of the column is going to be the full spacing, which is about 21.3 feet. We're saying that all the columns are W14 by 61, grade 50, and they're being loaded in the strong axis direction. So more information, let's just say for this project, you want to design for low level of protection. Since this is a column, it's going to be a primary component. We're going to use single degree of freedom, and we're going to use SBITs. You could use the energy solution, but again, it's depending on whether or not you are in the pressure control region or the impulsive region. And you're in that middle zone, those approaches are not going to be accurate. We're going to include the axial load, which was specified already as 67 kips, and it's assumed that it includes the equivalent static reaction from the roof member plus the effects of gravity in using this load combination 1.2D plus 0.5L, which is the typical way you will do it, because you have the load acting on it, and then the blast response can cause that additional load that gets thrown into the column. Cladding weight, we're assuming that is about 10 psf, again, and it spans horizontally between the columns. So the first step we do is we calculate the inputs that we're going to need to put into the SBIT. So we know that the load is coming at an angle into our column because it's at a third floor. So we calculate the angle of incidence, which is generally measured from the normal of the element under analysis. So in this case, it's the inverse tangent of 37 by 85. So we have an angle of incidence of about 24 degrees. We're saying that the columns are continuous floor to roof, so the bottom end it's restrained against rotation. So we're going to treat it as a fixed condition. At the top, we don't have that continuity, so we're just going to treat it as a simple condition. We're going to analyze the column as a fixed simple. For now, we're assuming that it's a flexural response, but we're going to double check that later. And then these are the span, the grid spacing or the tributary width, the axial load acting on the member, and the supported weight, of which is the aerial weight of the cladding. Again, the way you add the supported weight into a single degree of freedom system is you need to think of in terms of like, if this element moves, what mass around it is going to be moving with it. So in this case, since the cladding is connected to the column, if that column is trying to move, it's going to pull the cladding with it. So it's all going to be deflecting together, and it's all going to be contributing to the inertial resistance against the blast load. So the first step we do in the problem is we define the load. We enter our charge weight and standoff. Remember, we take the slant distance. We take the slant distance to the very top of the middle of the columns, and we enter our degree of incidence. Then we define the element, which is our span is 15.4 feet. Our spacing, we said it was 21.3 feet because it represents the grid spacing, column to column. And right here, we define our column 14 by 61 in the strong axis, and these are all the cross-sectional properties. Here's where we add our supported weight, 10 psf, and here we pick the strength of the member. Here we add the axial load acting on the column, and then here I wanted to show this. SBES allow you to account for an eccentricity depending on how your connection is detailed, and that includes the P delta effects. The way the P delta effects are included in SBES are a little bit different than using the magnifying factor approach from the AISC code, because that presents some complications when you get into the plastic range. So what SBES does is it calculates an equivalent lateral load, uniformly distributed load, that gets applied at every time step that causes the same effects at that P delta every time that it gets deformed. So depending on the detailing of your connection, you can see right here, you can include that, and SF will take into account the P delta effects for that case. Next, with the information that was entered, SBES will calculate the moment capacity, and the difference between the positive and negative moment capacity because of the on-brace length. It takes that into account, and it also calculates the ratio of the axial load to the capacity. As you can see, we're clearly under the 20%. So our flexural assumption was right. So when we pick our response limits, we're going to treat it as a beaming flexure. Low level of protection, primary element, we're only allowed to go to 3 degrees of rotation and a ductility of 3. These are the natural period of the element, which is 24.86 milliseconds. This table right here is the single degree of freedom properties that SBES calculates based on the inputs of the geometry and the member size and the support conditions. And right here we have the resistance function. It is a fixed simple element, so this first point in the plot is that first hinge that occurs at the fixed end, and then you have an additional strength until you reach that middle hinge at midspan when the collapse mechanism form, and at that point you're just sort of like deforming plastically with no additional resistance. So you run the analysis and you get a support rotation of 1.7, ductility ratio of 3.1, which exceeds the value of 3, although I will say right here, in an actual design, you probably, it's close enough, you'll probably say that is okay in terms of flexural response. What I wanted to show here, though, is that the shear capacity of the member is not adequate to resist the shear load associated with the ultimate moment capacity of the member. So in this case, you will recommend that column be, if it was an existing building, you will say, hey, we need to add a wet plate or something to increase the shear, or if it's a new design, you may actually end up changing the component. Here's some additional plots from SBES. You can see the displacement versus time history. We get a peak deflection of about 2.6. We can see the blast load and the apply static load, and we can see the dynamic peak reactions. The red line is the dynamic reactions at the fixed support, so it's pulling more load, and the blue line is the dynamic reaction at the simple support, which is pulling less load. And again, I'm not going to go over this in detail, but this is just a summary of all the different features and capabilities that SBET has. So let's just talk about frames, which is the very last point in the outline. Generally frames are not required to be designed for blast resistance because they have an inherent resistance to blast load. The main reason for that is, if you look at this plot on the right, the natural period of frames in terms of like their sway motion, which will be the T, it tends to be very large. And the duration of the blast loads, as we saw, it's in the millisecond range. So the ratio of T over TD tends to be really large. So when you look at a triangular load, this plot is for a triangular load, which is what we assume for blast load, the effects approach zero. So that's the main reason that once a blast load hits a frame, the effects get sort of like dissipated and you don't need to look at the response. Maybe when you have some smaller buildings with very long duration loads, you could sort of like look at it, and that's more typical of petrochemical applications. But generally, you don't have to look at the lateral response. The different approaches for frame analysis, the first one, which is the more simplistic one, is when you take the equivalent static loads from your facade elements and you apply them as lateral loads on your building. Or you could actually do a single degree of freedom representations of your frame. You may use simple equations that are available from structural dynamic books to determine the single degree of freedom parameter of your frames, or you can use structural software to do pushover analysis and determine that resistance function. So for example, in the first approach, if this was our building, we know the facade is spanning floor to floor. We can calculate the equivalent static loads, which are the red arrows, and apply them laterally, and then just use a typical static lateral analysis to determine our bracings and our foundation loads. The next approach, it's the single degree of freedom. Like I said, you may use simple calculations from structural dynamic books, or you can do a pushover analysis, for example, using SAP 2000, in which you apply the lateral blast loads, you make sure you include your gravity loads, and you push the building to develop your resistance function. You need to make sure that you account for the mass. The advantage of this approach is that once you develop a resistance function for a given frame, you can run different blast loads faster and get a better idea for an envelope response. Finally, when in more sort of like sophisticated and higher fidelity cases, you can just use a structural dynamic software where you use hinges to account for nonlinearity, and you apply the load dynamically, and then you can see the full response of the building. In this case, we were looking at a brace frame, and we put a blast load on it and just push it to the very end, and we can see how the braces fail. So you see these hinges forming, and that will be the sort of like you can go a step further if you use like Dyna or final element modeling, but generally this level should give you a pretty good result in terms of analyzing the blast response, the full blast response of a frame building. And I think that brings us to the end. Thank you so much for your time. I think I had to rush it a little bit at the end, but hopefully you got a pretty good idea of what the blast resistant design of steel building takes. Thank you.
Thank you very much, Aldo. I think we have time to answer a few questions. Just as a reminder, if you've not yet chatted in your question, you can still do that. We have a few questions on this example here related to the axial load that you're applying. The first question is, does this include the blast load on the roof?
on the example, I mean the example, the axial load should include the blast reaction from the components. So it should include the blast load on the roof. So in this case, we applied the equivalent static reaction from the member, and also added the gravity load that it was acting on the roof. That's what the assumption was in the example.
Okay, great. So this P here, as you mentioned here, includes the dead load, the live load from the roof, as well as the blast load.
Correct.
Okay, great. Thank you. Next question that we have, are documents such as UFC 34002 and others that are UFC available to engineers without a security clearance from the DoD, such as engineers designing blast buildings in petrochemical facilities?
I think those are for official use only. I can actually, if you email me that, Christina, I can double check that. And generally, you do not need a clearance. I think I could be wrong, but the main thing is that you have a government project, so that you can request the document. So you have a need to have it. Is that you need to have a government project to request a document. But I don't think you have to be clear. But I will confirm that. I'm not 100% sure on that.
Okay, and then and similarly, can you describe where some of the software and other design manuals can be obtained for blast design?
Yes, I think SBETS, you can go to like I can send you this in an email. It's like the whole building design guide website or the PDC website, and you can request it. I know for SBETS you do not need a clearance. You just need to have a government project. SAP 2000 is another commercially available software that you can use for blast design. And the design guidelines, they're all the UFCs are mainly available at the PDC website, which I can provide, and you can send a list to the attendees. The different documents for the different industries, like the ISC and the VAs, they all have to be requested to them once you have a project that requires that document. I don't think you can request it if you don't have a sort of say like a need to know per se.
Okay, thanks. So for those of you that had questions about that, we will, Aldo will give me some information on links where you can find that.
I will make sure that I double check with because I'll be honest with you, a lot of times, we get those documents because we're all clear here, and you just kind of like take it for granted. But if you send it to me, we'll make sure that we will send you a sort of like a written reference on how to go and get those documents, and I just need to clear it with our SFO here in the company.
Okay, great. And then the next question, can you suggest a reference for design using composite steel members, and what additional factors would you have to consider when you use composite steel members? And this is composite steel with concrete.
Right. Yeah, the latest version of the SBETS methodology manual included a whole module on composite design. So in terms of recommending a reference, that will be one that comes to mind that I'm familiar with it. I'm not sure that I follow the part about like the safety factors. Generally, you approach it in a similar way where you will calculate a moment capacity using the typical approaches that you use for static design, and based on that, you develop your resistance function based on that dynamic capacity. Obviously, you're going to have some controlling parameters like you do when you don't want to, so you're going to be controlled by the compression area or by yielding of the steel. But in general, if I'm understanding correctly, it's no different than the other types of design in which you follow the classic sort of like code approaches for determining your moment capacities, and then you turn that into a resistant function or stiffness, to develop your single degree of freedom curve.
Okay, thank you. And I think we have time for, we'll take one more question. Do you include an increase in the modulus of elasticity due to a high strain rate? And the second part is, if we increase the average strength compared to the yield, won't this be unconservative if the material is at the limit of the yield stress, for example, 50 KSI?
Well, we do not increase the modulus of elasticity, and I don't understand the part about the conservatism. I mean, the reason that we put the dynamic increase factor is because the strain rates, this is responding so fast that your component is going to be effectively stronger than what that lower value is. So the other thing to keep in mind is, like, just because you reach that, whatever we call the yield point, with or without the DIF, it's not really a failure. I mean, at that point, you're deforming plastically, and if you design your connections right, you shouldn't have any sort of like component like suddenly flying into your room, because your connections will remain attached. So again, it's a little bit of a difficult question. I'm happy to follow up with the person that asked it and provide some additional information. But that's sort of like the approach. Where you want to account for those strain effects, because otherwise it will be too conservative and it will be inefficient to design for blast loss. You're going to end up with really sort of like heavy sections.
Okay, thank you. Unfortunately, that's all the time we have today for questions. Looks like there's quite a few questions we didn't get to, so we will work with Aldo to send a response to you by email.